Again, Geometry Scholars, here we are. We are on officially the first lesson of Chapter 8. So we're going to take the dilation and similarity information from Chapter 4 transformations, and we're going to apply it to the polygons that we've been working with, like in Chapter 7, triangles, quadrilaterals, any other polygon. So when we talk about the word similarity, it's not quite congruence, because it doesn't preserve length, but it does preserve other parts. And so we're going to talk about how we can write similarity statements just like we would write congruent statements previously. So hopefully by the end of this little video, you'll be able to use similarity statements, find corresponding lengths in similar polygons, find parameters and areas of similar polygons, and decide whether polygons are in fact similar. This should be a little bit familiar because you have covered this in previous years of schooling. So let's get started. Recall from section 4.6 that two geometric figures are similar if and only if there's a similarity transformation that maps one figure onto the other. Again, that can be like a dilation. It can be a combination of them as well. So here's our core concept. Corresponding parts of similar polygons in the diagram below, ABC is similar to DEF. You can write that triangle ABC is similar to triangle DEF as triangle ABC with a squiggly, and that's like the top of a congruence symbol. So ABC is similar to triangle DEF. A similarity transformation preserves angle measure. So corresponding angles are congruent. A similarity transformation also enlarges or reduces side lengths by a scale factor k. So corresponding side lengths are proportional. That's the same k that we were talking about in 4.5 and 6. So if you take a look and they're the same direction, then A is similar to D, C is similar to F, B is similar to E. And you'll see that they're marked, the measurements are congruent. The ratios of the sides are also equal to k. So if you look for some structure, notice that any two congruent figures are also similar. So triangle LMN and triangle WXY below, if the scale factor is 5 over 5 equals 6 over 6 equals 7 over 7 equals 1, then you can write that triangle LMN is congruent to triangle WXY. But you can also write, if the side lengths are the same, triangle LMN is congruent to triangle WXY. But that's only if you have both the angles exactly the same and the sides exactly the same. So here's how we're going to use these statements.
In the diagram, triangle RST is similar to triangle XYZ. Part A, find the scale factor from triangle RST to triangle XYZ. Part B, list all pairs of congruent angles. Part C, write the ratios of the corresponding side lengths in a statement of proportionality. Solution. Part A, to find the scale factor, compare the ratios of the corresponding sides. First, identify the corresponding sides. Side XY corresponds to side RS. So XY divided by RS is equal to 12 divided by 20, which equals 3/5. Side YZ corresponds to side ST, so YZ divided by ST is equal to 18 divided by 30, which equals 3/5. Side ZX corresponds to side TR, so ZX divided by TR is equal to 15 divided by 25, which equals 3/5. So the scale factor is 3/5. Part B. In similar triangles, corresponding angles are congruent. This means angle R is congruent to angle X, angle S is congruent to angle Y, and angle T is congruent to angle Z. Part C. Because the ratios in Part A are equal, you can write XY divided by RS is equal to YZ divided by ST, which is equal to ZX divided by TR. In a statement of proportionality, any pair of ratios forms a true proportion.
So proportions was a very big part of your 7th grade math experience. And a proportion, remember, is a ratio equal to a ratio. So any of these will equal that. It says write the ratios. And a statement of proportionality, just remember, means a fraction equal to a fraction, a ratio equal to another ratio. So the next core concept in 8.1 is that corresponding lengths in similar polygons are equal to the scale factor. So if two polygons are similar, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor of the similar polygons. Just so we know, corresponding lengths in similar triangles include side lengths, altitudes, medians, and midsegments. So it's not just the outsides. Here's some examples.
In the diagram, triangle DEF is similar to triangle MNP. Find the value of x. Solution. The triangles are similar, so the corresponding side lengths are proportional. This means you can use a proportion to find the value of x. Use corresponding sides NP and EF and corresponding sides MN and DE to write a proportion. One proportion you can use is MN divided by DE is equal to NP divided by EF. There are several ways to write the proportion. For example, you could write the proportion DF divided by MP is equal to EF divided by NP. In the proportion MN divided by DE equals NP divided by EF, substitute 18 for MN, 15 for DE, 30 for NP, and X for EF, which gives you the proportion 18 divided by 15 is equal to 30 divided by X. Use the cross products property, and 18x is equal to 450. Solve for x by dividing each side of the equation by 18, and x is equal to 25. The value of x is 25.
Just to make sure you understood, even though they wrote mn over dE, mn over dE equals np over ef. You could also write mp over df. As long as you have a proportion like this, both of them are valid. You'll get x equals 25 both ways. Okay, here's another example.
In the diagram, triangle TPR is similar to triangle XPZ. Find the length of the altitude PS. Solution. First, find the scale factor from triangle XPZ to triangle TPR. To find the scale factor, you need to find the ratio of the corresponding sides. Look at the information given in the diagram. Use the corresponding sides TR and XZ to find the scale factor. So the scale factor from triangle XPZ to triangle TPR is equal to TR divided by XZ. By the segment addition postulate, TR is equal to TS plus SR, which is equal to 6 plus 6. XZ is equal to XY plus YZ, which is equal to 8 plus 8. Add, and 6 plus 6 is equal to 12, and 8 plus 8 is equal to 16. Simplify, 12 divided by 16 is equal to 3/4. You are given segment PS is the altitude of triangle TPR. Notice segment PY is the altitude of triangle XPZ. Because the ratio of the lengths of the altitudes in similar triangles is equal to the scale factor, you can write the following proportion. PS divided by PY is equal to 3/4. Substitute 20 for PY, and the proportion is PS divided by 20 is equal to 3 divided by 4. Multiply each side of the equation by 20 and simplify. This gives you PS is equal to 15. The length of the altitude PS is 15.
Now, once you're able to find those corresponding lengths, then we can further apply it to perimeter, which is all the way on the outside, and area, which is on the inside. Again, this is a repeat of a concept you've seen before, so hopefully it seems more familiar to you. We've got a theorem. If two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. It's going to be exactly the same. Here's a way you can state it. If KLMN is similar to PQRS, then if you add all those four sides together, it's equal to those ratios each side. If you analyze it, when two similar polygons have a scale factor of k, then the ratio of their perimeters is also equal to k. Here's an example.
A town plans to build a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25 meters. The new pool will be similar in shape to an Olympic pool but will have a length of 40 meters. Find the perimeters of an Olympic pool and the new pool. Solution. Step 1. Understand the problem. You are given the length and width of a rectangle and the length of a similar rectangle. You need to find the perimeters of both rectangles. Step 2. Make a plan. Find the scale factor of the similar rectangles and find the perimeter of an Olympic pool. Then use the perimeters of similar polygons theorem to write and solve a proportion to find the perimeter of the new pool. Step 3. Solve the problem. Because the new pool will be similar to an Olympic pool, the scale factor is the ratio of the lengths, 40 meters to 50 meters, or 40/50ths, which is equal to 4/5. Because an Olympic pool is rectangular with a length of 50 meters and a width of 25 meters, the perimeter of an Olympic pool is 2 times 50 plus 2 times 25, which is equal to 150 meters. Write and solve a proportion to find the perimeter x of the new pool. Use the perimeters of similar polygons theorem, which states if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. Let x represent the perimeter of the new pool, and write the proportion x divided by 150 is equal to 4 divided by 5. Multiply each side of the equation by 150 and simplify. This gives you x is equal to 120. You can also write the scale factor as a decimal. In this example, you can write the scale factor as 8/10 and multiply by 150 to get x equals 8/10 times 150, which equals 120. So the perimeter of an Olympic pool is 150 meters and the perimeter of the new pool is 120 meters. Step 4. Look back. Check that the ratio of the perimeters is equal to the scale factor. The ratio of the perimeters is 120 divided by 150, which does equal the scale factor, 4 divided by 5.
See a little check mark? Always make sure you check. And I'll bet some of you actually could do the 0.8 times 150 in your head because you're smart like that. Okay, we're going to do some more examples there. However, now we're going to talk about area. Area is slightly different. We have a theorem. If two polygons are similar, then the ratio of their areas is equal to the squares of the ratios of their corresponding side lengths. Because remember, area is length times width. Okay, so we're talking 2 dimensions. So if you have one ratio, it's this way, right? But then if you have another ratio, it's this way. So you multiply them. That's how you remember it's squared. Analyzing relationships, when two similar polygons have a scale factor of k, the ratio of their areas is equal to k squared. So that's the big takeaway here. Perimeters is just k, but area is k squared.
When two similar polygons have a scale factor of k, the ratio of their areas is equal to k squared.
I don't know how I pressed that, but dude's voice came on. Okay, here's another example.
In the diagram, triangle ABC is similar to triangle DEF. Find the area of triangle DEF. Solution. Because the triangles are similar, by the areas of similar polygons theorem, the ratio of the area of triangle ABC to the area of triangle DEF is equal to the square of the ratio of AB to DE. Write and solve a proportion to find the area of triangle DEF. Let A represent the area of triangle DEF. Use the areas of similar polygons theorem to write the proportion area of triangle ABC divided by area of triangle DEF is equal to the quantity AB divided by DE squared. Substitute 36 for the area of triangle ABC, A for the area of triangle DEF, 10 for AB, and 5 for DE. Square the right side of the equation. This gives you 36 divided by A is equal to 100 divided by 25. Use the cross products property, and 36 times 25 is equal to 100 times A. Simplify, and this gives you the equation 900 equals 100A. Solve for a by dividing each side of the equation by 100, and 9 is equal to a. So the area of triangle DEF is 9 square centimeters.
When you're looking at this picture, that actually makes sense. If this one's 36, this looks like about a fourth, which is 9. Also, if you're doing this right here, you don't necessarily have to square the 10 and the 5. You could, if it does divide the 10 by the 5 to get 2. 2 squared would give you 4, which, as you can see, 100 divided by 25 is 4. You'd get the same answer, just another way to do it. Moving on, examples in class. And then last, if I give you a bunch of pictures, you should be able to take those measurements and decide whether they are similar using those theorems.
Decide whether ABCDE and KLQRP are similar. Explain your reasoning. Solution. To show the pentagons are similar, you need to show that corresponding side lengths are proportional and corresponding angles are congruent. Compare the ratios of corresponding side lengths. KL divided by AB is equal to 8 divided by 12, which is equal to 2/3. LQ divided by BC is equal to 6 divided by 9, which equals 2/3. QR divided by CD is equal to 4 divided by 6, which equals 2/3. RP divided by DE is equal to 6 divided by 9, which equals 2/3. PK divided by EA is equal to 8 divided by 12, which equals 2/3. So corresponding sides of the pentagons are proportional with the scale factor of 2/3. However, this does not necessarily mean the pentagons are similar. Compare corresponding angles using transformations. A dilation with center A and scale factor 2/3 moves ABCDE onto AFGHJ. Then a reflection moves AFGHJ onto KLMNP. KLMNP does not exactly coincide with KLQRP because not all the corresponding angles are congruent. Only angle A and angle K are congruent. Because angle measure is not preserved, the two pentagons are not similar.
So 2 things you should notice here. Number 1, these are reflections of each other. So when they compared QL to CB, they're on the opposite sides. So make sure they're facing the same direction. And then second, you do have to make sure that, again, the angle measurements are preserved because otherwise they're not similar, as you can see. And we're going to do probably like 12 different examples in class where I have a whole page full of those where you can look at them and decide for yourself. And I believe we're at the end. Yeah, so there's a bunch of examples that you'll see in Big Ideas. And again, anything that you missed, just go over it again or ask in class.